So today I'm going to do a short video on how to use the latest software for SEELab. And when you launch the application, this is the window that you're presented with. It's an oscilloscope with two channels enabled by default, A1 and A2. The time-based controls are here, and you can see the time-base here. It goes up to 3 milliseconds by default, and you can increase it to, let's say, a very long time base. So let's say 1 seconds of data acquisition. Now, if I want to connect, let's say, a sine wave to the A1 input. So here I have the controls for the sine wave frequency. I'll take a small wire and just connect WG here to the input of the oscilloscope A1. So as soon as I've connected that, you see that the sine wave has appeared here. And if I set the time period to 2 milliseconds, I can see that from here, 1 millisecond, I have one complete waveform, and I have another complete waveform up to here, because the sine wave frequency is 1000 Hertz. And I can also find that out by curve fitting A1 with a standard sine function. So it says the frequency is 999.5, nearly 1000, and the amplitude is 3 volts. So if I adjust this, I'm able to vary the frequency as well. Okay, so if I set it to 500 Hertz, for example, yeah, there you have one full waveform in 2 milliseconds. Now on the left here, you have the trigger settings. So the sine wave generator is essentially a voltage reading, a voltage value that oscillates between -3 and 3 volts. And your oscilloscope measures these as a function of time. So it takes this, a snapshot for 2 milliseconds. Now that could start here, which will give you this shape, or it could start here, which will give you this, or it could start here, which will give you this. So if the trigger is off, you will find the waveforms jumping around. But this is difficult to, analyze or even just look at. So what you do is you trigger on CH1, you say, start measurements when the voltage reaches near 0 volts. So once it reaches here, it'll take a measurement. Now for your next cycle, even if it's here, it'll just wait a little bit till it reaches near 0 and then take one reading. So you have overlapping plots. So that's your function. And you have a cursor here where you can drag this vertical line and it'll tell you what the value here is. So let's see, here it's -3 volts and here it's +3 volts. So that's your cursor. You can also freeze the oscilloscope and take single shot readings. Right now here you have 3 voltmeters, capacitance measurement, frequency measurement, sine waves frequency adjustment. You also have a square wave SQ1, so let me connect that to A2. You can see that as well. So A2 I've enabled, and I'm going to give it some frequency. There you go. Let's take a little time base there. So SQ1 is now 200 Hertz. It's a 5 volt amplitude signal, so I need to set it to 8 volts to be able to see the full signal. Now this is triggered on the sine wave, so that's why the sine wave is static. If I trigger on the square wave and I set the voltage level to something between the square waves levels, you see the square wave is now triggered. You can see the minor variations and fluctuations in the wave, but it's not jumping around. Okay, so that's a square wave. You can also set the duty cycle for the square wave, which is the amount of time it spends on and the amount of time it spends off, the ratio. So I see 90% duty cycle looks like this and 10% looks like this. And this is commonly used to adjust the intensity of LEDs. So all your LED lightings, they usually do this flickering thing with LEDs where you can't perceive the flickering, but you can see the net brightness, the average amount of current that flowed through the LED, resulting in the average amount of light. Now you have PV1 and PV2, which are voltage outputs. So if I set PV1 like so, PV1 is connected to A2. So I set PV1 to, let's say, 2.92 volts. A2 is at 2.92 volts levels. And here you have this voltmeter also telling you that A2 is at 2.92 volts. And similarly, PV2 I can set to, let's say, 1.04 volts. Here it's 1.04 volts. And here as well. And if I set the time base long enough, right, I can actually study the variation as I move these sliders. See that? So the scope is running independently of these controls. So you can use both of them together. I think that covers usage of the oscilloscope. We've looked at freeze. We've looked at this A1, A2 minus A1 is a differential signal. It's a 10-bit oscilloscope by default, but if you're only using one channel, it goes to 12-bit. So that gives you a cleaner data. So here, let's say I have, okay, so my sine wave is connected to A2, but the A1 channel is sort of special. You can map it to other channels as well. So that's why you have this setup here where I've connected the wire to A2, but because I've mapped it here to A2, I'm able to view the signal right here. Okay, so now let's look at briefly what else is there on this application. So under the device menu, you can choose which device to open if you have multiple SEELab devices on the same computer. You have a circuit simulator, which will open on your web browser simulator. There are some samples. This also deals with the simulator. This is a programmer's reference manual. If you want to write some Python code, it takes you to the reference manual. There's the Internet of Things, which is a place where you can upload sensor data globally and view it on the cloud as plots and stuff. Visual programming is a programming interface where you don't type code, you attach blocks together to form code constructs. That's also going to open in a browser. You have some school level experiments, simple things like DC voltages, how to measure a DC voltage with this device. And here, let's say I connect A1 to 5 volts. So it's going to show me 5 volts. I don't have a battery handy. So the laptop that I'm using is only giving 4.93 volts. This is very expected. It's within only a small percentage. So it won't be exactly 5 volts. But if I look at CS1, so I'll get 3.33 or 3.32, very close voltages. Or if I connect it to PV1, whatever value I set on PV1 is going to be shown there. Now, let's say I pick resistance by Ohm's law. So you make this circuit and then you can vary PV1, click and drag, and whatever you apply to PV1 because of this network, you'll get some readings, whatever. Now you have different experiments, electrical, I have sound, mechanics, sensors. Now write code. This lets you write code. Let's say get voltage from A1. So this is an embedded Python notebook where you can write simple code and try out things. So let's say I take an example here. There's some examples that are given. Capture 1. So it says capture from A1 1000 points with 10 microseconds delay between each point, and just simply run this and you have these readings here. I can also do %matplotlib inline to get the plots within my notebook here itself. And all of these experiments, the oscilloscope, everything, you can edit the code. So if you're not happy with, let's say, the trace color that I'm using, right, or the background color, let's say I don't want this foreground color, whatever, small changes. Let me take an example here. So this is a gray colored pen. I won't make it red. So this is going to be 0, 0. Just as a simple example. So you see my trace is now red. So you don't have to download the source code and go through all that trouble. You have the code right here, just edit and simply run it. And you can make all those changes on the fly. Well, this is a little big and complex, but you have simpler programs which you'll be able to edit. The spreadsheet simply opens up a small spreadsheet here, which lets you enter data into 2-column form. Very useful for stuff like IV characteristics, where you want to enter readings manually and plot them and see what happens. And the device menu we've covered. Theme, inline plots, install packages, options. Yeah. So I think that covers the oscilloscope. Thank you for listening.